A black hole begins when gravity overwhelms every other force. A massive star spends most of its life fusing lighter elements into heavier ones, releasing energy that counters its own weight. For millions of years, equilibrium holds. But eventually, fuel runs out. Fusion stops. The light that supported the outer layers fades. Gravity, unopposed, pulls inward. The collapse accelerates, crushing the core to densities beyond atomic structure. Electrons merge with protons, forming neutrons. Even neutron pressure fails for the most massive stars. Nothing stops the implosion. The matter falls until it occupies a region so dense, so compact, that escape velocity exceeds the speed of light. The star vanishes from view. A black hole is born. From the outside, the black hole is defined by its event horizon, the boundary through which no signal can return. This is not a surface one can touch. It is a mathematical threshold in space-time. Light approaching it curves inward. Time, as measured by an external observer, slows near it, redshifting all emitted radiation toward darkness. To the infalling matter, however, the crossing feels ordinary. Nothing special marks the horizon itself. But once crossed, all paths lead inward. There is no route back. Einstein's field equations describe this geometry exactly for a simple, non-rotating case, the Schwarzschild solution. The entire external structure depends on one parameter: mass. A black hole's radius is proportional to that mass, about 3 kilometers for every solar mass contained within. Add spin, and the solution becomes the Kerr metric, introducing an ergosphere, an oblate region outside the horizon where space is dragged around by rotation. Particles entering the ergosphere can, in principle, extract energy from the hole through the Penrose process. Add charge, and the metric expands to Kerr-Newman, though astrophysical holes carry negligible net charge. What lies beyond the horizon is unknown. The equations predict a singularity, a point where density and curvature become infinite, and the mathematics fails. Such infinities signal not physical reality, but a breakdown of our theory's domain. At those scales, quantum effects must dominate. We do not yet possess a complete theory of quantum gravity to describe it. The singularity remains the blank center of the black hole problem, a boundary not only in space, but in knowledge. Black holes are detected not by their light, but by their influence. A companion star may orbit an invisible partner whose mass exceeds any plausible stellar remnant. Gas pulled from the companion forms an accretion disk, heated by friction and compression to tens of millions of degrees. This gas emits X-rays and sometimes radio waves before it disappears past the horizon. Jets of charged particles, collimated by magnetic fields, shoot outward from the poles, sometimes stretching for thousands of light years. These outflows can influence entire galaxies, distributing energy into interstellar space. There are several classes of black holes. Stellar mass black holes form from individual stars. Intermediate mass candidates, hundreds to thousands of solar masses, inhabit dense clusters and dwarf galaxies. Supermassive black holes, millions to billions of solar masses, lie at the centers of nearly all large galaxies. How such enormous masses assembled so early in cosmic history remains an open question. They may have started as smaller seed holes that grew rapidly by accreting dense gas, or merged repeatedly during the chaotic youth of the universe. At the core of our Milky Way resides Sagittarius A, a black hole about 4 million times the mass of the Sun. Infrared telescopes track nearby stars whose orbits trace invisible ellipses around this center. One star, S2, completes a full circuit every 16 years, reaching speeds over 7,000 kilometers per second at its closest approach. From its motion, we infer the mass and compactness of the unseen object. No cluster of dark stars could survive so dense a packing. Only a black hole fits the data. To 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, the one in galaxy M87. By linking radio observatories around Earth, they created a virtual telescope the size of the planet, resolving details on the scale of the horizon itself. The image showed a bright, asymmetric ring surrounding a dark center, the silhouette of the event horizon against glowing plasma. The brightness pattern matched predictions from general relativity. d'extreme regime. Inside a black hole, classical reasoning reaches its limit. General relativity predicts that all matter collapses to a point, but quantum mechanics insists that uncertainty forbids perfect localization. Reconciling these principles is the goal of quantum gravity. We know certain boundary facts. Black holes radiate and they possess entropy proportional to the area of their horizon, not their volume. This was Stephen Hawking's great insight in the 1970s. Quantum fluctuations near the horizon cause particle pairs to form. One escapes while the other falls in. To conserve energy, the whole loses a tiny bit of mass. The radiation is thermal with a temperature inversely proportional to the mass. Large holes are cold, small ones are hotter. Over unimaginable timescales, they evaporate. A stellar mass black hole would take roughly 10 to the power of 67 years to vanish, a number so vast it dwarfs the current age of the universe. This radiation introduces the information paradox. If a black hole evaporates completely, what becomes of the information about the matter that fell in? Quantum mechanics forbids information loss, yet the Hawking radiation, if purely thermal, carries none. Possible resolutions include holographic storage, information encoded on the horizon's surface, or subtle correlations in the outgoing radiation. No consensus exists. Experiments cannot yet probe such faint effects. Whatever the answer, it will link gravity, thermodynamics, and quantum theory in a deeper framework. On larger scales, black holes are engines of galactic evolution. When gas falls into a supermassive black hole, the resulting radiation can outshine the entire host galaxy. These luminous centers, known as quasars, were first observed in the 1960s. They reside in the distant universe, their light emitted billions of years ago. Quasar activity is most common in young galaxies, implying that black holes grow rapidly during early cosmic times. The energy they release can drive winds that push gas outward, regulating star formation and establishing a balance between black hole mass and galactic mass. Observations reveal a tight correlation between the mass of a galaxy's central black hole and the velocity dispersion of its bulge, a relation called the M-sigma law. This link suggests coevolution, galaxies and their black holes shaping each other through feedback. Even dormant black holes affect their surroundings through gravity alone. They bend the paths of passing photons, acting as gravitational lenses. When a black hole moves in front of a background star, the star's light is magnified and distorted, producing a temporary brightening. Such microlensing events reveal isolated black holes adrift in our galaxy, remnants of long-dead stars. Future surveys will measure how many wander unseen between the stars. The mathematics of black holes continues to refine. Numerical relativity solves Einstein's equations on supercomputers, modeling collisions, accretion flows, and tidal disruptions in detail. Analytical work explores near-horizon geometry, membrane analogies, and conformal symmetries. Quantum field theory in curved spacetime predicts phenomena like Hawking radiation, Unruh temperature, and horizon thermodynamics. Together, these approaches turn the black hole from a singular mystery into a precise, testable object of physics. Yet the mystery persists. Do singularities always remain hidden behind horizons? The cosmic censorship conjecture says yes, preserving determinism, but in certain theoretical scenarios, rapid rotation, exotic matter, the horizon might fail, exposing a naked singularity to the universe. If such objects exist, they would mark a direct breakdown of predictability. So far, none have been observed. There are also speculative structures called wormholes, tunnels through space-time mathematically related to black hole solutions. Whether nature builds them remains unknown. Most would collapse instantly without exotic energy to hold them open. Still, their study informs our understanding of space-time topology and quantum entanglement. In some modern interpretations, a wormhole is a geometric expression of entanglement itself, suggesting deep links between information and geometry. The connection between black holes and thermodynamics runs deeper than metaphor. The four laws of black hole mechanics mirror the four laws of thermodynamics. Surface gravity behaves like temperature. Horizon area corresponds to entropy. The conservation of energy aligns with mass. Jacob Bekenstein first proposed that a black hole's entropy equals 1/4 of its horizon area in Planck units, a staggering quantity. For a single solar mass black hole, that entropy exceeds that of all ordinary matter in the observable universe combined. This insight implies that information content scales with surface area, not volume, a principle that led to the broader concept of holography in theoretical physics. Observations continue to sharpen. Gravitational wave astronomy now surveys the sky in space-time rather than light. Future detectors such as LISA will observe lower frequency waves from merging supermassive black holes across cosmic history. Radio interferometers will resolve horizon-scale features more clearly. High-energy missions will study X-ray reverberations from disks, mapping the geometry near the inner stable orbit. Each instrument extends human senses deeper into the invisible. In the distant future, when stars burn out and galaxies thin, black holes will dominate what remains. White dwarfs will cool, neutron stars will fade, and only black holes will persist, slowly radiating their stored mass. Over trillions of years, they will evaporate. The final moments of a small black hole's life end in a brief flash of high-energy particles. When the last one disappears, the universe will enter its dark, dilute era, low-energy photons expanding endlessly. The geometry of space-time will flatten. Entropy will reach its maximum. The story will continue only as temperature drifts toward absolute zero. For now, the universe is young enough that black holes remain creative forces. They regulate galaxies, test gravity, and link the visible to the invisible. They remind us that emptiness can have structure, that darkness can reveal law, and that the boundary between the known and the unknown is often mathematical. Every measurement of a black hole is a test of Einstein's equations. Every unresolved paradox is a clue toward the next theory. To study a black hole is to study the nature of reality itself, space, time, energy, and information intertwined. No myth or metaphor is required. The equations are enough. They describe a universe in which gravity can curve light into circles, freeze time at a surface, and connect the quantum world with the cosmic. In that sense, black holes are not anomalies, but the natural outcome of simple principles carried to their limits. They are the geometry of gravity made visible. They are the places where physics becomes self-aware. They are reminders that the unknown is not elsewhere. It is built into the structure of the cosmos, waiting behind every horizon.